If decay constant lambda is given, then we need to find the probability of decay of the nucleus and the mean lifetime of the nucleus. So probability of decay. So probability of being decayed is the number of particles that get decayed divided by total number of particles. So number of particles decayed in t time is n naught minus n upon n naught, where n is our standard number of particles that are left after t time. So this is n naught minus n naught e to the power minus lambda t by n naught, which gives this our answer. So this is the probability of any nucleus getting decayed by the time t has passed. In second part, the mean lifetime. So we have n is equal to n naught e to the power minus lambda t, our standard equation. Now let's see first in dt time how many particles get decayed at a given time t. So for that we'll do dn by dt. So dn by dt is minus n naught lambda e to the power minus lambda t, which gives dn is equal to this much. So this is the change in number of particles, which means these many particles have decayed in dt time at a given time t. Now dn is a negative quantity because number of particles keep decreasing, which means if we talk about the number of particles decayed, then we have to put a negative sign because that should be a positive quantity. So these particles minus dn number of particles, they have a lifetime of t because at t time they are getting decayed. So now we can write the t average for all the particles. So this number of particles have their lifetime t. So if we just add all such particles and multiply them by their lifetimes and divide by total number of particles, so this will be the t average. So again, n is n naught e to the power minus lambda t. From here we got in dt time these many particles get decayed with a negative sign. So if minus dn particles have their lifetime as t, then the average lifetime of all the particles, so that is minus dn into t and just summation of that. So minus dn1 into t1 plus minus dn2 into t2 plus minus dn2 into t3, like that. That is integral of minus dn into t. Divide by total number of particles n naught, and limits will be t from 0 to infinity. And when we solve this integral, we'll get our answer 1 by lambda. So next slide we'll see how to solve this integral, but otherwise the concept part is here. Now the integral. So we need to solve this integral. T average is 0 to infinity lambda e to the power minus lambda t dt. So we'll do a substitution of lambda t as x. So our equation simplifies to be 1 by lambda integral of x e to the power minus x dx. So this will solve by using the integration by parts, which is u dv is equal to d of uv minus v du. Now in x e to the power minus x, we'll take u to be x, and e to the power minus x dx will take to be dv. So what we have given here is u dv, and we'll write that in the form of d of uv minus v du. So for that, of course, we'll need to know what is du and what is v. So du will be dx, and v, so if we integrate this, v will be minus e to the power minus x. So we put these values here, and what we get is t average 1 by lambda d of uv minus integral of v du. So this term, so it's integral of d of something, so this term will completely come outside, and integral of e to the power minus x dx is simply minus e to the power minus x. The limits are same, 0 to infinity, and this, so when it is 0, then this term is 0, and at infinity we are going to use L'Hopital because both numerator and denominator will tend to be infinity. So So differentiate numerator denominator both and put the value of x is equal to infinity, and you will see that comes to be 0. Minus minus 1, which gives the answer t average to be 1 by lambda. So this is the mathematical part, otherwise our problem is solved here. So after that it's just the integral, we solve it and get our answer.